Hello, here's a couple of practice questions in quantum physics. We're starting here with a photoelectric cell is an electronic device that can detect photons. Figure 4.1 shows a cross section through a simple photocell. So we've got a photon coming in, this line here, which is coming down onto the metal plate. Then we've got an electron being emitted going over to B, and all this is in a tube, which I assume is going to be evacuated. What we've got, a metal plate A, coated with potassium in an evacuated transparent tube. Excellent. Photon entering the tube, absorbed by the plate, causing one electron to be released from the surface going towards a collector rod at B. Fine. So photon in, photoelectric effects, electron out, off to B. State the name of this process. All right, just have. So that's the photoelectric effect. Part 2. Potassium has a work function of 3.5 times 10 to the minus 19 joules. Define the term work function. So the work function is the minimum energy required to release an electron from the surface of the metal. So you have to make sure you've got the minimum energy required to release an electron from the surface of the metal. From surface of metal. So nice to get an easy definition. Another mark there. Calculate the threshold frequency of potassium. Right, so remember what's going on with threshold frequency then. So that is just giving us that minimum energy to get an electron released. So that is to do with the work function, because our photoelectric equation, our HF, our energy of the photon coming in, is equal to the work function plus Ke max. Now, in case of the threshold frequency, we have no kinetic energy. We're just releasing the electron. So HF0 is equal to the work function. So that's what we're going to be using here to get our threshold frequency. We're doing the work function, 3.5 times 10 to the minus 19 is what they've given us, divided by the Planck constant. So 6.63 times 10 to the minus 34. Whack that into the calculator and we're getting 5.279, so 5.3 times 10 to the 14 hertz. So far so good. Part 3. The photon incident on plate A has a wavelength of 4.2 times 10 to the minus 7 meters, so visible. Show that its energy is about 5 times 10 to the minus 19 joules. So our energy, well, HF, or we can write that as HC over lambda, just replacing the frequency with the speed over wavelength. So we just got to stick all of these numbers in now because they've given us, yeah, we've got all of this. So we're going to have, I'm not going to write them all out, 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8, and then divide by the wavelength, which is the 4.2 times 10 to the minus 7, is giving 4.7 times 10 to the minus 19, which is pretty close to what they wanted for joules. That's a 19. Okay, so that's good. Calculate the maximum kinetic energy of the electron emitted from the potassium surface. Right, so that is the energy of the photon. We now take off the work function because we're just using this equation over here. Take off the work function. What was the work function again? 3.5 times 10 to the minus 19. And that is then going to give us, well, 1.2 times 10 to the minus 19 joules. That is our maximum kinetic energy. Right, there's more to this question if I remember rightly. An electron is released with 0 speed from plate A. It's accelerated from plate A through a PD of 12 volts to the metal rod at B. State the increase in kinetic energy of the electron in electron volts. Okay, so we've got a energy then. So if we've got 12 volt PD, so the energy is going to be 12 electron volts if we've accelerated an electron through 12 volts, we get 12 electron volts of energy. And what am I then trying to do here? I've got to state the increase in kinetic energy of the electron in electron volts. Well, there we go. That is 12 eV. Show that this increase is about 2 times 10 to the minus 18 joules. So we just multiply 12 by 1.6 times 10 to the minus 19. And then that comes out as, what we got, 19.2 times 10 to the minus 19. So 1.92. So 1.9 times 10 to the minus 18 joules. Okay, right, that was just checking if you know what an electron volt is by the look of it. Calculate the speed of the electron as it hits rod B. So we've got that a half mv squared, our kinetic energy, is the 1.92 times 10 to the minus 18 joules. So V is going to be the square root of, well, we want to double that. So what's that? 3.84 times 10 to the minus 18. And then divide by the 9.11 times 10 to the minus 31 for the mass of the electron. Square root it all. And right, that's definitely going to have to be in the calculator. So just give me a moment to type it all in. 2.1 times 10 to the 6 meters per second. Last part of the question. The photocell is connected to a 12 volt DC supply through a very sensitive ammeter. Light of wavelength that shines on the plate. Plate absorbs that amount of light energy every second. 1% of the absorbed photons cause electrons to be emitted. Estimate the current in the circuit. Okay, right, so we've got then, so what is this? We've got that wavelength. We're getting that amount of light energy every second, and 1% of that is then getting absorbed. Right, okay, so we've got how many photons are we getting then? So we've got 1.2 times 10 to the minus 6. That's our total energy. We need to then divide by the energy. Is that the wavelength we had before? I'm just wondering if this is the same number. I think it is. Is this the one we had before? Yeah, this is our the energy that we worked out, the 5 times 10 to the minus 19. So 4.7 times 10 to the minus 19. So 4.7 times 10 to the minus 19 joules. Yeah, because we used that wavelength when we worked out what the energy was. So I've just taken that from the previous part of the question. So that is giving us 2.55 times 10 to the 12 photons per second. That's what we've got there. We're getting 1% of those photons are being absorbed. So we're getting 2.55 times 10 to the 10, that's a 0, 10 to the 10 electrons per second are going to be emitted, because it's a one-to-one interaction between photons and the electrons, and we've got 1% of the photons. So our current then is going to be, so we multiply that by 1.6 times 10 to the minus 19, and that will give us our current. So that's coming out at 4 times 10 to the minus 9 amps. Okay, right, that was a nice little question to finish on, that one. I like that last part. So that's the first question. I'm only doing 2 in this. So what have we got next? We've got a parallel beam of red light of wavelength 6 times 10 to the minus 7 meters from a laser is incident normally on a diffraction grating. Okay, right, so we're starting with diffraction grating. And right, I've just drawn that out. Bright red spots are observed on a curved screen placed beyond the grating. Diffraction grating has 300 lines per millimeter. Show that the separation D between adjacent lines of the grating is 3.3 times 10 to the minus 6 meters. So 300 lines per millimeter means that we've got, so 300, and we need to go to from millimeters to meters. So 300 per millimeter, we need to multiply by 1,000 to get the number we got per meter. So that's lines per meter. So we want to then do 1 over that will give us the separation. So separation is going to be equal to 1 over 3 times 10 to the 5. So 1 over 3 times 10 to the minus 5, all in all, because I've just taken the 10 to the 5 and done the reciprocal of it. So yeah, that's 3.3 times 10 to the minus 6 meters. Fair enough. Okay. Calculate the angle theta at which the first order red spot is seen. So our so first order spot on this, so we need our diffraction grating equation. So that's sine theta is equal to n, that's the order of the spot, times the wavelength divided by d, which is our separation. So we're going for n is equal to 1 here because we're going to the first order. So we got 6.3 times 10 to the minus 7. That's our wavelength. Divide by the separation, 3.3 times 10 to the minus 6. So that gives us 0.19. And inverse sine of that is just short of 11 degrees. So around about 11 degrees, the two significant figures. So that's good. A lot of people don't remember that equation. It's in the formula booklet anyway. But yeah, it's one that doesn't tend to stick in the mind that well. The screen curves around the full 180 degrees in front of the grating. Explain why there are 11 bright spots. So what they're saying here for 11 bright spots is we've got the central one and then 5 on either side. So the maximum we can get, so the maximum value of sine theta is equal to 1. So we want to see what n is going to be when we've got sine theta equal to 1. So n is going to be equal to d over lambda. So we're just doing 1 over this. Well, we can see this is going to be, seeing as that came out at just less than a fifth, this is going to be just more than 5. So n is going to be equal to 5 point whatever it is. So the maximum integer value of n is equal to 5. So that means we've got straight on and then 5 in either direction. So yeah, bright spots equals 1 straight on and then plus 5 up plus 5 down, which equals 11 spots. So that's good. Again, I think there's more of this one. And there is. Calculate the energy of each photon of light emitted by the laser at a wavelength of 6.3 times 10 to the minus 7. So we're having to go, instead of using our HF, we're using our HC over lambda. So we're just using Planck constant, speed of light, divided by the wavelength. It's just straight to the calculator. And that is giving me 3.157. It's always 10 to the minus 19 with the numbers we've got here, so I won't bother putting those in the calculator. So yeah, 3.2 times 10 to the minus 19 joules, so 2 eV. The number of photons emitted each second to produce a power of 0.5 milliwatts. So we've got 5 times 10 to the minus 4 watts. So that's our joules per second. We want photons per second, so we just have to divide by the 3.2 times 10 to the minus 19. Well, I used the 3.157 rather than the 2 to get a better answer, which is 1.58 times 10 to the 15. So 1.6 times 10 to the 15 photons per second. So these are pretty standard calculations thus far. Right, the last part then. A beam of electrons in a vacuum can travel through a thin sheet of graphite perpendicular to the beam to produce diffraction pattern of rings on a fluorescent screen beyond the graphite sheet. Yes, explain why this pattern is produced. Right, okay, these ones are always a little bit tricky for these. But again, don't worry about stating what seems to be the obvious. So let's start off then and say that electrons have wave behavior, because we've got diffraction. So we want to say clearly then that if the electrons are diffracting, that we've got some wave behavior. So let's make a statement of that. We can then say how we're getting, obviously don't actually put bullet points on these, but you can just write these out as sentences. Electrons have wave behavior. Then we can say the gaps between the atoms in the graphite, are similar to the, roughly equal to the wavelength of the electrons. Obviously put that in full words, I'm just putting this in shorthand. So therefore diffraction occurs, or significant diffraction occurs. What else are we going to want to say? We're going to want to say that we've got regular spacing. This is another thing. If we want to see a nice sharp diffraction pattern on the screen, then we want the graphite to act like a diffraction grating. So regular spacing of atoms in the graphite means that it acts like a diffraction grating. So acts like a diffraction grating. So yeah, we can see we're piecing this together. I just think this is one of the more difficult ones to piece together. And then we want to say, well, why have we got rings? Because they've said here we've got a diffraction pattern of rings. We've got so far as to say why we're getting a diffraction pattern. You know, the electron's behaving as a wave. We're getting lots of diffraction because the wavelength of the electron is similar to the spacing. We've got regular spacing, so it's acting like a diffraction grating. But then we want to say that we're getting rings in pattern because the spacings are in all directions. We got all possible orientations because the slits, in inverted commas, in the graphite are at all possible orientations. So there's no favoured direction in this, so that's why we're going to have to see a ring. So no favoured direction, because if we weren't seeing rings, if we were seeing actual bands, then that would be suggesting that there's a favoured orientation in the graphite, but we're not actually getting that. So you end up with circles. We get that symmetry. You know, it's like when we're doing geometry problems. If things are symmetrical, we end up getting lots of circles turning up. No favoured direction. Yeah, so we're covering a lot of stuff there, but I think it's a more complicated one, as I say, for actually describing that as to why this is being produced than it is with some of the other explanations. So yeah, just write those out in full sentences without the bullet points there and without the shorthand. Right, we've got a calculation to end up now that I've filled up the whole screen. Calculate the speed v of electrons with a de Broglie wavelength of 5 × 10⁻11 meters. Right, so our de Broglie wavelength, let's squeeze this one down the bottom, that's Planck constant divided by momentum. So Planck constant divided by m times v. So if we want to get v, our speed of the electron, then we want to be doing the Planck constant divided by the de Broglie wavelength multiplied by mass of the electron. So Planck constant 6.63 × 10⁻⁴. I'll just say this while I'm typing it into the calculator. Then divide by the mass of the electron, 9.11 × 10⁻31, and the de Broglie wavelength, which was, where was it, 5 × 10⁻11, which is giving 1.46 × 10⁻⁷ meters per second. So 1.5 × 10⁻⁷ meters per second to two significant figures. Right, and what potential difference do we need in order to accelerate electrons to that speed? So that means charge on the electron multiplied by potential difference V, That's our joules per coulomb multiplied by coulombs. That will then be half mv squared. So we know, well, we know everything on this, don't we? We've got the v squared. Well, actually, we can just use this formula again. So let's type it all in without any approximations on this. Our v is going to be equal to, this is capital V, we want the PD. So it's going to be a half times m times h squared over wavelength squared, mass squared, so we can cancel those. And yeah, we're just sticking that into the, oh, I've got to divide by the E, haven't I? Because I had an EV on the other side. So we're doing h squared over 2e lambda squared m. That's going to be our potential difference, which is coming out at, it's quite a lot to type in actually, quite a lot of numbers here. So what was that one? That was that, and then, oh my word, and then 2.5 times 10 to the minus 600 volts. Right, that was quite a lot to type in at the end, but yeah, it's coming out pretty much 600 volts. Yeah, so there we go, quite easy calculations at the end. This is the thing with the quantum section, the calculations are pretty straightforward because we're just doing the same thing over and over again. We're doing de Broglie wavelengths, we're doing photoelectric equation, and we're accelerating up a few electrons, doing our EV is half mv squared. Not a lot there. The descriptions are a bit more fiddly. But yeah, nice couple of practice questions there.